that you have 100 slides. Is that true?
Oh.
Okay, are we set up? Okay, our next speaker is Dr. Chang, who will continue along similar lines.
Can you hear me?
Speak louder.
Okay. First of all, I would like to thank the organizer for giving me the chance to present our work here, and especially that my talk can be arranged to follow Professor Robert Schrock's talk, because I'm going to talk about the work collaborated with him, okay, as you just heard. And here is the outline. We will consider the Parse model partition function on lattice strips, and we know that the flow polynomial and reliability polynomial are a special case of Parse model partition function. And we also consider a restricted Parse model. Here, restrict means we consider the two variables of the Parse model satisfy the two-dimensional phase transition condition, and we look at the zeros. And we also consider the zeros of the Parse model partition function in the large Q limit. Here, Q is the number of states of the Parse model. And as I have, I guess, more slides than Professor Robert Schrock has, and I have only half the time he has, and I cannot speak as fast as he did. So,
but you can push the button fast.
Yes, that's right. So I'm going to skip many material. I'm not going to give you very detailed proof or explain things in detail. I will just show you the main results we obtained. Okay, so let me don't repeat the definition, but just tell you the notation I use here. So this capital Q is number of states for the Parse model, and this little n is the number of vertices, number of edges, and we consider the zero field Hamiltonian. So we have only two variables. One is the number of state Q, and another variable is V, which is exponential beta j minus 1. So basically, it is the temperature variable. Okay, and when V goes from 0 to infinite, it corresponds to ferromagnet with temperature from infinite to 0, and for V from minus to 1, it corresponds to antiferromagnet with temperature from 0 to infinite. Okay, and as you just heard, we can define the free energy per side, and we also know that the Tott polynomial can be expressed in terms of this summation of spanning subgraph. So if you compare with this Fortran-Catlin expression for the Parse model partition function, it is also a summation of the spanning subgraph. So there is a certain relations between Tott polynomial and Parse model partition function with some prefactor, and change of variable x is equal to 1 plus q over v, and y is equal to 1 plus v. And we know that there is a duality symmetry for a planar graph. The Tott polynomial is equal to the Tott polynomial of its planar dual if we switch these two variables x and y. Okay, and we know that at spatial value of x and y, we have this number of spanning trees, number of spanning forests, and so forth, but I'm not going to talk about this today. And we also know that when V is equal to 1, which is 0 temperature plus antiferromagnet, it is equivalent to the chromatic polynomial with no prefactor, so they are exactly the same. Okay, and as you just heard, we can define the ground state degeneracy per vertices. Okay, and there is a relation between the Tott polynomial and chromatic polynomial if we set at x equal to 1 minus q and y equal to 0 with some prefactor. And for the flow polynomial, we consider nowhere zero float, and this flow polynomial can be a special case of Tott polynomial or Q-state Parse model. So here we set x equal to 0 and y equal to 1 minus q. So if you compare with this expression for the chromatic polynomial, we found that for the planar graph, the flow polynomial is basically the chromatic polynomial of its dual, and with this factor 1 over q. Okay, so the study of the flow polynomial on the planar graph complement the calculation for the chromatic polynomial. Okay. And for the reliability polynomial, again, we heard many times, and we have this all-terminal reliability polynomial, which is a function of p, which is the probability that each edge is present. Okay, and because this is all-terminal reliability polynomial, so it is a summation of connected spanning subgraph. So therefore, it corresponds to the top polynomial with x equal to 1, or path model with q approach to 0. So because of these limits, we may need to use L'Hopital rule in certain calculation. Okay, and the relation, and we set this v equal to p over 1 minus p here, change of variable here. So the physical range of this p, which is between 0 and 1, correspond to q equal to 0 path ferromagnets with temperature from infinite to 0. Okay, and of course we know some basic property of the reliability polynomial. And here are the lattice we consider. So we will mainly consider square lattice strip here, triangular lattice, honeycomb lattice, and self-dual strip of square lattice. So this strip, it is a self-dual, and it is like a cyclic square lattice strip, but with an extra vertices with edges connected to these edges on a boundary. And we were going to take the length of this strip Lx to infinity and keep this width Ly fixed. Okay, so these are the lattice type we consider, and we have considered all sorts of boundary conditions: free, cylindrical, cyclic, Mobius, toroidal, and Klein-Bottom. And because we take Lx to infinite and keep Ly fixed, so cylindrical is a little bit different from the cyclic boundary condition. Okay, and here is the result. As this strip repeats itself, you see, if we consider cyclic boundary condition, we just have, this is just a tree, right? And another tree, and have this bond connecting them. Okay, and if we consider toroidal boundary condition, we just have a circuit in each slide, and we connected them in this way for the square lattice, and different way for other lattices. Okay, so because this graph repeats itself again and again, so we have this partition function given by this expression, which is a certain coefficient times this lambda raised to Lx power. Okay, and we found that for the cyclic boundary condition, these coefficients are particularly simple. They can be expressed in terms of Chebyshev polynomial of the second kind. Okay, so I just list the first few of them here. And this coefficient have interesting property that they have a Braha number with odd index as one of their roots. So for example, we have root q equal to 1, or one of these root is b5, and so forth. And for the square lattice with self-dual boundary condition, we found that the coefficient again can be expressed in terms of Chebyshev polynomial, which we call them kappa. And the first few of them are listed here. And again, this coefficient kappa, they have a Braha number of an even index as one of their roots. So for example, we have q equal to 2 as one of these kappa 2 roots, and q equal to 3, which is Braha number 6, b6, and so forth. Okay, and so here is the example which was done by Biggs and others more than 35 years ago. And we know that the chromatic polynomial of the cyclic ladder graph, which corresponds to the square lattice with width 2, and which has this expression. So we see that we have this coefficient 1 here, q minus 1, q squared minus 3q plus 1 here, which are this coefficient I just showed you. Okay, and I'm not going to talk about how the coefficients switch from cyclic to Mobius today. Anyway, and here is another example for the triangular strip with width 2 and cyclic boundary condition. And for the full temperature Potts model partition function, again we have coefficient 1, okay, which is C0, C1, and C2, and there are 2 lambdas with coefficient 1, and 3 lambda with coefficient C1, and 1 lambda with coefficient C2 here, and so forth. And here is another example which I just showed you the zeros and the accumulation set of these zeros when we take the infinite length limits. This is the result for the honeycomb lattice with cyclic boundary condition with width 3. So we see this locus separate this complex plane into several regions. And if we increase the width, we go to Ly equal to 4, and again honeycomb lattice, we have this figure, and with 5 we have this figure. And so as Professor Rob Shark just mentioned, this Q sub C defined, which is the largest real value, this locus cross the real axis, it increase, and presumably it will increase to the two-dimensional result when we have very infinite width. Okay, and here we consider the summation of these coefficients. Okay, especially let's consider the cyclic boundary condition. For example, as I just mentioned, each slide for the cyclic boundary condition is just a tree graph. So the summation of this coloring configuration should be just the chromatic polynomial of a tree graph, which is q times q minus 1 raised to Ly minus 1. Ly is the width of the strip. Okay, and for example, for the toroidal boundary condition for the square and triangular lattices, each slice is a circuit. So the summation of this coefficient will be the chromatic polynomial for a circuit, which is given by this expression, and so forth for other. These are the results for the chromatic polynomial. But if we consider the full temperature Potts model partition function, there is no restriction that adjacent vertices cannot have the same color. So in this case, either cyclic or toroidal boundary condition, the summation of this coefficient should be q raised to L1. Okay, since we know the summation of this coefficient and we know the expression of this coefficient, we can determine how many coefficients with CD as their coefficient. Okay, so we solve for this and we got this table. Okay, so for example, for the example I just showed you, this is for the full temperature Potts model partition function, and with 2, we have 2 lambda with coefficient 0, 3 lambda with coefficient 1, and 1 lambda with coefficient 2. So that's just the example I just showed you here. 1 lambda here, 3 lambda here, and 2 lambda here. Okay, and if we sum over this number of lambdas, we get the capital N, which is the total number of lambda, is given by 2 Ly choose Ly, which asymptotically approach to 4 raised to Ly's power when Ly is very large. Okay, so these results are valid for arbitrary widths. And we can do the same thing for the chromatic polynomial. We know the summation of the coefficient, and we know the expression for CD, so we can solve for these numbers. So here's another table for the chromatic polynomial and square and triangular lattices. And the total number of lambda is given by this expression, which is asymptotically approach to 3 raised to Ly's power when Ly is large. Okay, and we can do the same thing for the honeycomb lattice, and we get another table. And we can do the same thing for the cyclic self-dual strip of the square lattice. We know the coefficients are given by those kappa I just showed you, so we can solve for them and get this table for the number of lambda, and the expression for this total number of lambda is given by this simple expression here. And this table is for the full temperature Potts model partition function, and we can do the same thing for the chromatic polynomial for this self-dual square lattice strips. Okay, and Jacobson, Salas, and Sokos has also considered these strips with free and cylindrical boundary condition, and these are the total number of lambda. So basically, this value here, which is the Catalan number for the free strip of the triangular lattice, it is just the, let me see, okay, it is just the first column in this table. Okay, this is the table for cyclic boundary condition, and first column gives us the number of lambda for the free strips. Okay, and similarly we can get this number of lambda for chromatic polynomial and triangular lattices. And for the square lattice, because of the reflection symmetry, so the total number of lambda can be reduced for the full temperature pulse model chromatic polynomial, and for the cylindrical strip we get all sorts of these numbers, and these two are conjecture, but I'm not going to talk about this in detail. And here's the table. Okay, let's go on to the flow polynomial. As we consider again the cyclic strips, so the flow polynomial for cyclic strip again have this CD as their coefficient and certain lambda raised to m's part. Here m is the length of the strips. Okay, and again by the coloring argument we know the total the summation of the coefficient should be given by this expression, because we can think of the flow polynomial on this planar graph as the chromatic polynomial of its dual strips, right? So by the same consideration we can get this table, okay, for the flow polynomial on this cyclic strip of square and honeycomb lattices. Okay, and here let me just show you some zeros and their accumulation set. Okay, it is more interesting to consider the cyclic boundary condition. Okay, we have this coefficient 1, C1, C2 here again, and these results are the same as what Reed and Royal obtained for the chromatic polynomial of the dual graph of this Ly equal to 2 cyclic square lattice graph. Okay, so this locus cross Q equal to 2 and 3, if we go to with 3 and square lattice, again this locus cross Q equal to 2 and 3, and this locus go to infinity. Okay, and we can do the same thing for Ly equal to 4. This locus again cross real axis at Q equal to 2 and Q equal to 3. And we can do the same thing for other boundary condition, but let me just skip all these things. And we can do the same calculation for triangular lattices and other lattices. Okay, so let me skip all this. Okay, anyway, we have done several calculations for different kind of lattice with different boundary conditions. So let's go on to the reliability polynomial. So if we consider this strip again, this reliability polynomial again has such kind of expression, some coefficient times some, here I call it alpha raised to the length of the strip. Okay, and from the result of the two-dimensional phase transition pulse model, we expect that the P sub C, which is the point where this locus cross the real axis, should be 4/3 for the square lattice and 3/2 for the triangular lattice. And we found that for the square lattice and with Ly equal to 2 here, this crossing is exactly 4/3, which is what we expect for the two-dimensional lattice. Okay, and we also found that for the reliability polynomial, this locus doesn't depend on the longitudinal boundary condition as the chromatic polynomial does. Okay, and we have done other width of the strips and different boundary condition. And let me skip this. Okay. So for the triangular lattice, we found that for the smallest width, Ly equal to 2, this locus B is given by given as shown here in this figure, and the crossing of this locus is at at p equal to 3 which is what we expect for the two-dimensional lattice. So for the smallest width, we already got the p sub c we expect for the two-dimensional infinite lattices. Okay, and we can do the same thing for the honeycomb lattices and self-dual strip of the square lattice. Okay, let me skip this. Okay, and as you heard in the previous talks, and we know that Royal and Sokol found a counterexample to violate the Brown-Coburn conjecture, which states that the zero of this reliability polynomial should lie inside this disk, absolute value p minus 1. Okay, and we just generalized their counterexample. So we have this K4 and with this edges replicate 6 times, repeat again to form a strip. Okay, so if we consider infinite length of this strip, we have the we got 0 look like this, and so the violation occurs here. Okay, so the tip of those arcs are at this point, which have absolute value p minus 1 equal to 1.0053 or something. Okay, so the violation is small. However, there are infinite number of zeros violate the conjecture, since this is the accumulation set. So there are infinite many zeros here. Okay, and we can do another generalization of the counterexample. Instead of replicate edges in the transverse direction, we can replicate the edges in the horizontal direction, and again we found the violation occur here. Okay, and however the violation of the Brown-Coburn conjecture is again it's very small. It's p minus 1, absolute value is about 1.0015, and so forth. And here is another example of the generalization of the counterexample, and again the violation occurred around here. Okay, let's go on to the next topic. We consider a restrict path model, and as I mentioned in the beginning, we consider these two variables q and v satisfy the phase transition condition. So for the square lattice, we set q equal to v squared. For the triangular lattice, we set q equal to v squared times v plus 3. Okay, and it is interesting that as you are going to see, this locus will cross the Braha number. Okay, for the strip with cyclic boundary condition or self-dual strip of the square lattice. Okay, and so let me just show you the figure. So here is an example for the square lattice with free boundary condition and width 2. On the complex V plane, this locus cross V equal to minus 2, but corresponding plot on the Q plane, this cross Q equal to 3. And this is the general feature we found for all the lattices and the boundary condition we consider. This locus always cross Q equal to 4. Okay, and it is more interesting to consider cyclic boundary condition. And for the smallest Ly, which is a circuit graph of the square lattice with cyclic boundary condition, the locus cross the real axis at q equal to 0 and q equal to 4. And for width 2, this is V plane, so let's look at Q plane. So this locus cross the real axis at q equal to 0, 2, and 4. Okay, which are so q equal to 2 is the Braha number with index 4, right? So if we increase the width of the cyclic strip, we found that the locus will not just cross 0 and 2, but cross 3, which is Braha number 6, and so on. Okay. So similarly for the triangular lattice, similarly for the triangular lattice, if we substitute that phase transition condition, and let's look at this figure. So, so for the triangular lattice with cyclic boundary condition and with width 2, we see the crossing of the locus at q equal to 2, q equal to 0, q equal to 2, q equal to 4, and so on. If we keep increase the width of the strip, this locus will cross those Braha number with even index. Okay, and if we consider the self-dual strip of the square lattice, we found that, for example, for the width 1 self-dual strip of the square lattice, which is the wheel graph, the crossing of the locus is at q equal to 1, q equal to 4. If we consider width 2 strip on the q plane, we have crossing at q equal to 1 and b5 and 4. And if we consider next width, we get crossing at Braha number b3, b5, b7, and so forth. If we keep on increase the width, we have more and more crossing at the Braha number. Okay, so finally the last topic I'm going to talk is the zero of the path model partition function in the large Q limit. So we found it is very interesting that if we arrange the terms of the path model partition function in decreasing power of v in this way. So in general, these terms are complicated, but if we only keep the first term and last term for the square lattice when Q is very large, it is very interesting that these zeros are approximately located on the circle defined by, if we just keep the first and last term of the partition function. Okay, however, because I'm going to take Q to very large, so we change the variable to x. We will look at the 0 in the x plane. X is v divided by q raised to 2 over kappa, and this kappa is the coordination number. So for the square lattice or conglomerate lattice, it's just v over square root q. For the triangular lattices, it's v over q raised to 1/3 power. For the honeycomb lattices, it's v divided by q raised to 2/3 power. Okay, so we believe that if we consider very large strip or lattice and also very large Q, these zeros will merge onto the unit circle, the absolute value of x equal to 1. And even for the finite lattice section, if we don't take the thermodynamic limit, if we only have finite size of lattice, and as long as Q is large enough, for the square lattice, as I just mentioned, we just keep only the first and last term of the partition function, and we found it will give us very good estimation of the location of the zeros. So here is the figure for the square lattice. You see, if we only consider width 4, length 9, square lattice section, and with Q equal to 1000, the zeros are approximate located here, and we have very good estimation by just keeping the first and last term of the partition function. And this another circle is just the unit circle that when we have larger and larger Q, this zero will approach to this unit circle. And we have done this for various boundary conditions. And for the triangular lattice, this zero shift to the left a little bit. And for the triangular lattice, we, let's see. For the triangular lattice, we approximate the location of 0 by this expression. And for the honeycomb lattice, we approximate the location of 0 by this very simple expression when Q is very large. And we find these approximations are very good for the triangular lattice. See, this 0 shift to the left, but the approximated location from those simple expressions give very good estimation of the location of zeros. And of course, it's the best for the toroidal boundary condition. And for the honeycomb lattice, this 0 shift to the right a little bit, but again, we have very good estimation for the location of zeros. Okay, Okay, I think and we can do the same thing for the conglomerate, and there is no shift, and this 0 accumulate on a circle when Q is very large. Okay, so I think I will just stop here. Thank you very much for your attention.
When you consider the chromatic polynomial on self-dual square
Yes.
lattices, I believe what happens is that the external side, the external vertex will have some color.
Yes.
So it means that all of the vertices on the boundary will be able to take Q minus 1 colors. Right.
Yes.
So what I'm going to talk about in my talk tomorrow is a situation where all of those vertices on the boundary will take Q tilde colors, and those in the interior will take Q colors. So some of the structural properties that you show in one of your first slides, including these eigenvalue amplitudes, they will just come out as a special case of a thing that I will present tomorrow.
Yes, but at least if Q minus Q tilde is an integer, that's just equivalent to having an end graph, which is a complete graph, right? You just take, instead of putting one vertex, you have to just take a complete graph and connect it to.
Yes.
Yeah, okay, thank you very much for your comment. Yeah, we are looking forward to the talk tomorrow.
Was not really a question.
In your computation of roots of reliability polynomials, have you found,
Oops, I have
what's
to
the
go-
record for how far away from 1 you can get? Is there anything outside the circle of radius 1.1?
Well, it's your record, right?
Hmm?
You have the record.
No, it's Gordon.
I'm sorry, it's Gordon's record. Oh, yeah, 1.04.
That's the best known?
That's what he told me. Yeah, I asked him. I'm here.
Yeah, we didn't get very far outside of the unit circle.
So is there any chance that the zeros of reliability polynomials of graphs might be contained in some compact set, like the circle of radius 1.1 around that?
Right. Although I'm inclined to make the opposite conjecture. That they're dense in more complex planes.
One or the other.
Yeah, but I think so far the violation we found are relatively small.
I think the answer is we have no evidence one way or the other.
Well, I think what we found was that it's increasingly difficult to make them bigger, but we never failed yet. So, sort of diminishing returns. So if you've got a sequence where each successive term is smaller than the last, then does it converge or not? We don't know.
Okay, thank you.